Hi everyone. For this second lecture from chapter 29, we're going to talk about the net magnetic field from two long wires and also the force between two long wires that carry a current. So in the previous lecture, we talked about the fact that magnetic fields are created by electric currents, and we actually wrote down the formula for the magnetic field due to a long straight wire. Which is mu0 I over 2 pi r. So mu0 is the permeability constant that we talked about there. I is the current, r is the distance from the wire. And so what we're going to do here, we have two wires, one on the top here with a current coming into the board or into the page, right? Well, that's what the x means. And then one below at a distance d with a current coming out. And what I want is the net magnetic field right in the middle. So the point is here that magnetic fields are vectors, vector fields, and we need to add the vector components at each point from each current. So looking at the current from the top going in, using our second right-hand rule, thumb into the page, fingers curl around, the magnetic field from the top will be going to the left. Now, as it turns out, the same thing happens for the bottom current, but now it's coming out, so your thumb goes out and your fingers curl around. But at the point in between the wires, it is also going to the left. Right? It's curling kind of counterclockwise around this wire. So we've got two magnetic fields going to the left. Now we're saying they have the same current. So basically what's going to happen is you're going to add those two. They're going to have the same magnitude, mu0 I over 2 pi times 1/2 d, because right there, the r is 1/2 the distance from the d from the wire for each one. Now notice if I change the direction of one of the currents, maybe made this one go in, that field would go to the right, and the net magnetic field would be 0. They would cancel out. As it is in this case, though, we can add these together and write out negative I hat, meaning that the net field is in the negative x direction. So just doing that and adding those fields together, we get negative 2 mu0 I over pi d, again in the negative x direction. Now let's look at just a different point. Let's say we want the magnetic field down here at point B, a distance d from the bottom wire. Now the fields are going to be going in opposite directions. Right? The field from the top current, thumb going in, is going to be going to the left in the negative x direction down here. But the one from this one is going to be curling around, right, thumb out from the current. It's going to curl around in a circle and be going to the right. So the magnetic field from this bottom current is now pointing to the right. Right? It circles around and comes pointing to the right at that point. But again, we use the mu0 I over 2 pi r, but now that r is 2d from the top wire and only d from the bottom. And again, the negative I hat means for this wire, the current's going left, I hat going right for the bottom current. So then I can just add those together and I get the magnetic field 1/4 mu0 I over pi d. Again, the net field's in the x direction, positive x, because this current is closer, it's going to have a stronger magnetic field at point B. So you can see a problem where I've got to add the net magnetic fields. Now, I may have a situation where the magnetic field is not created by a long straight current, maybe created by a coil, right, a loop of current or something like that. I just have a different expression for the magnetic field. But once I know the vector direction, I can add magnetic fields as vectors. Another phenomenon I want to talk about in this lecture is the force between two parallel currents that carry wire, or carry two parallel wires that carry current. So we have an I1 here on the left, I2 on the right, distance d apart. Current I1 is going into the page, current I2 is coming out. Now, one thing that'll happen, I1 will create a magnetic field going down over here. So I'm going to call that B12, right? It's the magnetic field from current 1 at current 2. So it's pointing down. And we can calculate the magnitude just from our formula for a long straight current. u0 I1 over 2 pi d. And so this magnetic field is created by current 1. Now current 2 will create a magnetic field too. And you can figure out what its magnitude is over on I1. But we're going to concentrate now on what happens to current 2. Well, if there's a magnetic field there from the other current, it's going to experience a force, right? Our ILB type of force. So the force from current 1 on current 2, F12 is I2, the current of I2, times whatever the length of that I2 wire is, times the magnetic field it's experiencing, which comes from current 1, B12. So plugging in B12 here, and I notice the force is in the negative x direction. Okay, I've got the field going down. To get the direction of the force, I've got to go back and use my first right-hand rule. Fingers are going down, palm is out, right? The field's coming out of the page, so my force is that way, to the left, in the negative x direction. So just combining these and dividing by the length, right, so I can actually talk about the force per unit length on current 2, I get this expression, negative u0 I1 times I2 over 2 pi d. Now the negative again just tells me it's to the left. Now what about current 1? You could go backwards and you would see that the current from I2 creates a magnetic field that goes up over on I1. So we'll call that B21. Now it's going to have the same magnitude, except I1 is now I2, right? It's a different current creating the field. Now this magnetic field is going to create a force on current 1. Back to our first right-hand rule. Fingers into the page for the current. Palm is up due to the magnetic field, and your thumb is now to the right. So the force from current 2 on 1 is equal and opposite to the force from current 1 on current 2. Makes sense because it has to satisfy Newton's third law. So what you'll see happen if you have two currents with two wires with currents in opposite directions, they attract one another. There will actually be a force pulling them together. Now what if I flipped the direction of one of the currents? Maybe I made this current go in. Then they would repel each other. And maybe you can work through that and see how that works out. But either way, the expression for the force between the magnitude of the force per length is mu0 I1 I2 over 2 pi times the distance between the wires. Again, in this case, it's attractive. It can be repulsive if the direction of the currents are different. That will help you hopefully with one of the problems as well. And that's it for chapter 29. I will do a lecture on chapter 30 next here.